Our first speaker is Losey, and he's going to tell us about assistive robots.
So, hi everyone. I'm Losey. I'm a postdoctoral scholar at Stanford University, and I work with Professor Dorsa Sadiq. So I'm interested in developing robots that can help people in their everyday lives. And on the screen, you can see a picture of one of these robots, which is helping this gentleman who's had a spinal cord injury do rehabilitation exercises. One of the challenges when you're building robots for people is that every person has very specific needs, wants, preferences. And so we need robots that can embrace these differences, that can recognize how they need to interact with different people. I'm really interested in this problem of personalization. And my argument in my research is that in order to achieve personalization, we need interactions. When you have robots working in a close space with people, robots are able to see what people want, learn from these interactions, and then change their behavior to match the person's individual preferences. So my background is kind of a crossover between mechanical engineering and computer science. I'm trying to work with both fields at the intersection and working on human-robot interaction. So on the mechanical side, I'm using control and mechanics to bring humans and robots into the same space so that we can have these interactions in the first place. And then on the computer science side, looking more at learning, so that when the interactions occur, how can robots gather information and then use this information to make intelligent decisions? So today I want to talk about one project that has to do with personalization that I'm really excited about and I hope to tell you more about. That has to do with assistive robots. So kind of a staggering number, but in the United States alone, there are almost 1 million adults who have physical disabilities that need help every day doing simple tasks like eating. And the number for going to the bathroom, dressing, is even higher. So one obvious way to deal with this is having caregivers in the home or in a center that are helping these people do these tasks. But another exciting opportunity is developing robots, such as this wheelchair-mounted robotic arm that can help people every day. And here's a video of that same robotic arm in the home. And so the gentleman who's controlling this robot is trying to open a refrigerator door, grab some Tupperware, close the door, et cetera. And what I really want you to focus on in these videos is not only what the robot arm is doing, but also how this gentleman is controlling the robot arm. So you can see in the bottom right how he's using his hand. He's got a joystick, a 2-degree freedom joystick that he's moving around. And he also keeps doing this maybe seemingly strange motion of slapping the side of the robot. It might be first odd, why is he doing this? But remember that this robot is moving in 3-degree freedom space. The end effector alone has to do with position and orientation. But the joystick is only 2 degrees of freedom. So how is he going about controlling this at least 6-degree freedom robot using only a 2-degree freedom joystick? Slapping the side changes modes, so that in the first mode you control the XY position of the joystick, in the second you control the Z and the roll, etc. This is really challenging in practice. People spend up to 20% of their time working with these robots switching modes. And so we're excited about trying to develop ways that people can control these very high-dimensional systems in a simple and intuitive way. And we're using a data-driven approach, where first, we're going to collect offline demonstrations. Now, these demonstrations could be kinesthetic, such as the one I'm providing here. They could also be collected from other robots, or they could be provided by the user when they're controlling the robot using the strategy shown in the previous slide. Once we have these demonstrations of very high-dimensional motions, we want to learn an embedding into a lower dimensional space. So I was showing the robot motions of sweeping across the table and pouring. And here, I've embedded that down just to a 2-degree freedom joystick, where 1 degree of freedom causes the robot to move across the table, and the second causes this pouring motion. So overall in this project, the key idea is that we want to learn a very intuitive way to control high degree of freedom systems, such as assistive robotic arms, by embedding those high degree of freedom actions into a lower dimensional action space. How are we doing this? And what are things that make this intuitive? So there are 3 properties that we thought of that could be important, and I'm sure there are more, but these are the ones that we thought of so far that we want to make sure that our system has. The first one is controllability. Given some state that's in my training set, I want to make sure I can reach every other state that I've been shown at demonstration time. Another one has to do with consistency. So when I apply an input on the joystick, I don't want my robot to suddenly change directions. I want that one input to cause a similar action at the output. And that also ties into scalability. So the more I push on the joystick, ideally the robot will move faster or more in that direction. How we go about learning these models, we've actually tried a few different things. This is what we eventually came up with, and it's a conditional variational autoencoder. It's a self-supervised learning technique where the robot starts off with state action pairs. Let me see if I can use perfect. State action pairs that are provided at training time. These are collected during the kinesthetic demonstrations. It tries to embed these state action pairs into a latent space, Z. So Z here you can imagine as the person using that joystick. It might be 2 degrees of freedom. And then the robot tries to reconstruct those high-dimensional actions that it should be doing using just that low-dimensional input, Z, and the state that the robot's currently in. This state could be something like a camera, the arm's configuration, the positions of objects in the world, etc. So this is what we learn at training time. And then at test time, we give the person the ability to apply latent input Z using the joystick, and then we try to reconstruct these actions so that they can accomplish tasks. So all the person needs to do is control the joystick, and the robot realizes, oh, because I'm holding a cup and you're applying this latent input, I should pour, or I should lift this to your mouth, etc. So I want to give one simulation example just to kind of show the power of this technique, and then move on to some user studies. So in this simulated example, we have 2 5-degree of freedom robot arms that are working together to hold a box. So this is overall 10 degrees of freedom, and we're trying to push that down to just one latent dimension, where ideally this latent dimension will cause the arms to rotate the box in place. So here's what happens when you press left on the joystick. You're rotating the box, I guess, clockwise. And if you push more to the left, you rotate the box even more in that direction. Similarly, if you go right on the joystick, you're causing both of these 5-degree freedom robot arms to rotate the box to the right. And this is kind of the relationship we want to see. Remember, I mentioned how we have this controllability, this consistency, this scalability. This is a relationship between the person's latent input and the rotation of the box at the end effector. Ideally, we have a nice linear relationship where the more the person pushes, the more the box rotates. Cool. So to baseline this technique, we looked at a data set that's been provided by CMU. It's really interesting. I'd encourage you to check it out. It's this harmonic data set. And what it is, it's kind of collected on shared autonomy tasks where a person is trying to control a robot arm to pick up one of these 3 marshmallows, to stab it with a fork, and then to bring it to their mouth. So we're trying to figure out how our latent space can compare to this approach, which uses shared autonomy, where the robot knows these are 3 discrete goals. I'm reaching for one of them. I'm not sure which. And then as the person controls the robot, they figure out, oh, it's this particular marshmallow you want to reach. I'm going to pick that up. And I think the important thing here is that this is a discrete goal task, because the baseline methods, these shared autonomy methods, rely on having excuse me, a belief over the set of goals. So how often does the person get the marshmallow they wanted? These first 4 are from the baseline of how this is a success rate, or how frequently they get the marshmallow. The best one was this high assist method, which gets about 73% of the time. And then here's with our method. I do think there are some confounding factors, but at least we're excited that they both have a similar performance, where the person is really able to grab food and perform these really basic tasks, like eating in this scenario. But even more exciting than that would be to consider a scenario where we have continuous goals. Maybe I want to perform a continuous task like cooking. So we did this user study where people are, again, we're going to compare 2 different ways of controlling the robot. The first is the video I showed you at the beginning of the talk, where the person is slapping the side, or switching between discrete modes to control the end effector. The second is something that we've learned from data, this latent action approach. To give you some ideas of the feasibility, we trained on less than 7 minutes of kinesthetic demonstrations that I and my collaborators provided. These demonstrations were provided on task-related motions, but they weren't the task that we're actually going to test on itself. So similar, but slightly different. And also, the robot learned, it developed this model using an onboard computer without any GPU in less than 2 minutes. So an important part of this procedure is that we need to make sure that it's fast and doesn't require too much data, because we have a human in the loop. So let's just talk about the 2 different modes before we jump into the results. So here is what you would do if you're trying to control the robot with the end effector mode. You've got 2 joysticks. In one mode, when you've toggled this right button, you've got XYZ position of the end effector. And when you toggle to the other one, now you control roll, pitch, yaw. So you're directly controlling the twist at the robot's end effector using this strategy. And this is pretty comparable to what's already the state of the art. And then here's all you're going to have when you use the latent action approach. You only have these two latent dimensions to try to do these complex tasks. So in this first video, this person is trying to grab a carton of eggs that is on a shelf, pick up that carton, drop it in the bowl, and then pour it or release the carton into the recycling bin. This is all moving in a continuous space. On the left, you see the end effector approach, and on the right was the latent action approach. And these are the two different box and whisker plots of time. I'm going to replay that same video. This is at 3 times speed, just for some context. Yeah, we've kind of labeled what are the different parts of the task at the top. So you'll see the person gets really, I'm not saying the person was very bad at this task, but they got confused or exactly how to control the robot on the end effector side. So this is one example. We did several other tasks. Here they're trying to pick up this flour, again, pour it into the bowl, and now we turn it to the shelf. I think this is a really good example of how non-intuitive the end effector control can be, where this person really had no idea how to go about reaching for that flour. Yeah. And yeah, you can see that quite a big difference in time here. So what happens when we change the task or we move around obstacles? Like, how does this, I guess, generalize a little bit? So here we've got a slightly different task where you're trying to grab that apple on the top shelf, drop it into the bowl, and then stir. Stirring was one of the hardest things because everyone had their own definition of what stirring was. And my personal idea of, oh, this is stirring wasn't maybe obvious to everyone else. This is what this person thought was stirring. Again, there's a pretty big difference in time, and they're kind of confused on exactly how to go about reaching the apple. This final one maybe is the most interesting. We moved around the positions of the bin and also recycling bin, and we kind of also shifted the positions of this shelf. And then we put all 3 tasks together in a row without any sort of resetting. And yeah, tried to use both methods throughout. This one's slightly faster at 4 times speed. So yeah, I think one of the important things to remember is that we do have to stay somewhat within the set of demonstrations. So it's not like this person could use the robot to necessarily throw a baseball, because we've never shown anything like throwing a baseball before. I'm almost out of time, so just to wrap up, these are the manifolds that the robot moved in with the end effector and the latent action approach. You can kind of see how this is a constrained manifold, maybe smoother motions. These are some we asked the people afterwards, like, what did you think? Was it easier? Was it harder? What did you think of this method? Overall, we kind of saw a preference towards latent action approach, but people were a little bit confused by the autonomy. I don't think they really liked it as much as I thought they would. So yeah, I'll leave this up as I take questions, but yeah, I think the key here is that we can make high-dimensional systems easier to control by using a self-supervised learning to embed these high-dimensional actions into a lower-dimensional space. Thank you. Yeah, go for it.
So that was really interesting. I just wonder, when watching the user tap the side of the joystick, and I read a long time ago about other more natural methodologies of controlling things like that are not just joysticks. Mm-hmm. And then could you use robotic technology to sort of damp out the guy's instabilities and tremors and give him a more intuitive interface?
Yeah, thank you. Great question. So we looked at a joystick in this project, but the same methods would apply, for instance, if you were using EMG or EEG control, so that you could measure the person's muscle activation and then map that to the latent dimension. I think either of these would be really exciting and perhaps more intuitive ways for the person to control the robot. If they do have a tremor or some other source of high-frequency motion, it would be important to add some sort of filter, perhaps, to make it so that the robot moves more smoothly. We didn't do any pre or post processing here, but I do think that will be something important when we're actually using this with our patient population. But yeah, thank you for bringing that up.
All right, so Spencer from Amazon Robotics. So it's obvious that this is way better than people that have never handled an end effector before, but how does it compare? Like, a lot of people that use this will probably be using it for a long time on a day-to-day basis. How does your performance with the latency work against someone that is already familiar with how to perform the task and knows the ins and outs of moving the robot arm around?
Yeah, another really great question. Thank you for that. So I guess I have 2 points. The first, for the videos I showed, we sat the people down and gave them the controllers and told them to go without any practice. So they kind of had the same set of like background information for both the end effector and the latent space, just to try to make it fair. For the people who actually have purchased these systems and are using them out in the world, it's actually funny. So other groups have administered surveys to see how effective was this robot, how easy was it to use. And people actually said that they chose not to use this robot for things like eating because it was such a pain to use this in control mode. So yeah, I agree that people will adapt to the system and will maybe get better at using these controllers, but it seems like right now, just at a baseline, the control strategy we already have isn't working, at least not for all users. And just as a bigger point, I've kind of set these two things up as like opposite ends of a spectrum, but you could definitely imagine something in the middle where I'm switching between this toggling mode and a latent action mode, especially when I'm confused or I'm out of distribution with the latent actions. Maybe I could go back to the person directly controlling the end effector.
In the interest of time, let's take the other questions offline.
Yeah.
The speaker again.
Thank you, yeah.